Hello ladies and gentlemen, welcome back to GGS300. So this is going to be the third laboratory session which accompanies the third lecture, which was on descriptive statistics. So today what I need you to do is to go and find the R script which you can download from the Blackboard website. So let me just find where that is. So we need to go into lab. Once you're here, you want to find the lab2.r script, which hopefully you've been able to download. So essentially what we're going to be covering today are all those things which are affiliated with the lecture. So hopefully you've got the slides and you've managed to work through the lecture video as well. So what we're going to be looking at are the measures of central tendency, so the mode, the median, the mean. Then we're going to move on to looking at measures of dispersion variability, so the range, the quantile, different quantile functions, the standard deviation, variance, coefficient of variation, and then finally we're going to move on to looking at measures for shapes, for distributions, and also the relative position. And then at the very end, I'm just going to give you a short example of why we use the number of degrees of freedom. So you may remember when I was in the lecture I spoke about the fact that when we're sampling we use one fewer than the total number of sample data points within our sample, and that's to reduce bias. And I just give you a very short example of exactly why we do that using a small bit of code. Okay, so hopefully we'll be able to move on now. So you've got everything set up. What I want you to do first is to load the faithful data set. So let's just have a look at the faithful data set so we can discuss exactly what it is. So this is for the geyser, and essentially the geyser is in the Yellowstone National Park in Wyoming, and the data that we actually get for this data set is 272 observations for two variables, and one is the eruptions, so it's the eruption time in minutes, and one is how long you have to wait before the next eruption. Okay, so let's load that data set now and have a look. So here we go. You can have a look at this data now. So you can do this in your own R version. So this is the index on the left hand side here. This is I presume the eruption duration. And then this is how long you have to wait between the, so this is up to 3 minutes at a time. So actually quite a long eruption, but you might have to wait up to 79 minutes for that. So that's quite interesting. Okay, so you can take a look at that data. Here I've just printed it to the console. You could obviously actually just save specific variables within that data to the global environment up here. So you'll remember that we did this last time. So what I've done here is I've basically said I just want the eruptions variable. So I'm saying go to the faithful data set. Then I use a $sign in order to specifically say I want to capture that variable, that column, and then assign it to X, and then place X into the global environment. Okay, so up here you can see that's now it's a vector of all of those different eruption lengths. And what I'm able to do, given that we're focusing here on developing the descriptive statistics for specific data sets, is I'm going to develop the mode. So we're going to make we're going to carry out a couple of calculations in order to estimate what the mode is. So first we want to sort all of those data points. Okay, so sorting here is just literally arranging all the points so it goes from the very smallest values all the way up to the very largest values. Okay, obviously we want to look at our data before we actually make any assumptions about it. So I mean, it's fine to just kind of sort and print all of those values into your console and kind of take a look manually, but obviously we don't want to do that. We want to actually automate the mode value. We want the computer to basically tell us what the mode is, otherwise we would just do it by hand. So what we're able to do by plotting it is you're kind of able to get an idea of what the mode could potentially be. So here we've got a histogram. So we've been through this before in the first lecture and the first laboratory. So what we have on the x-axis is the time of the eruption. So we've got from 2 minutes here all the way up to 5 minutes. approximately, and then we've got all of the frequency of those values. So up to over 50 of the eruptions in our data set were under 2 minutes, okay, and then up here over 4 to 4.5 minutes, we've got probably up to about 80 different data points which fall into that data bucket. So it's quite a large number in that one there. And we can obviously specifically say how many individual buckets we want, or segments, whatever you want to call them, bins, within our histogram. Okay, so what I've done here is I've used 20 different bins, and then we start to get quite clearly a set of results. It's bimodal, so you'll remember you don't just have to have a single mode. Here actually it's kind of indicating that you probably have two kind of quite defined different peaks within the data set that we've got. Okay, so always start by plotting your data like this, and you can start to understand the underlying data characteristics. We actually do want to develop a way, though, for the computer to try and tell us what the specific answer is. Here what I've done is I've just generated a user-defined function. So this thing looks really horrible, but they're incredibly powerful. We did cover functions in the previous lab, and what I've done here is I've basically said, okay, I want to create a function, and I want to be able to give it a data set, which is a data frame, and I want to be able to allocate it to a function name called myMode. Okay, so whenever I call myMode, it's going to say, all right, myMode is a function. It requires a data frame, which is why here when I call it, I put the x, the data that we have, into it. Here it actually turns whatever you give it into a vector. So you could give it a different data structure and it would just convert it straight into a vector for you. It creates this z variable, and then basically what it does is it estimates, so it calculates the number of times that a certain data value occurs, and it tries to find the maximum number, and then it returns it as the mode. Okay, so when we actually run this self-defined function, it's saying, well, we've actually got 1.867, which is this first mode, this first peak over here, as one particular modal value, and then we've got 4.5, which is this second mode over here, as essentially the second modal value. Okay, so the data set is bimodal. It's got two specific modes that we're interested in, and what we've done is we've been able to plot and make an estimate ourselves for which we think those variables are, and then we've actually developed our own nifty little function in order for it to return to us the specific modes, essentially. Okay, so you remember that the mode is the most frequently occurring value, and now we've been able to calculate it in this specific way. Great, let's move on. So the median, you'll remember that the median is basically the middle value when you actually rank all of those data values that you've got for a specific data distribution. So here, what I'm going to do is I'm going to show you how to actually calculate that manually, and then we're going to look at how we would do that with a function as well. Okay. So we're taking the eruption data set again. So we've got 272 data values within this data set. We can actually sort these and allocate all of these values to x. Okay, so now they're all sorted. That's good, starting at the smallest value going up to the largest. And then what we're going to do here is we're going to say find the length of x, divide it by 2, and this basically is going to end up yielding like 136, I think. Yeah, there we go, 136. And what it's saying is I want you to give me the data value that's at 136 in the index 136 within the data frame. Okay, so if this is confusing to you, then just remember that it's basically just a data column. So let's just say that this is the index here. Like this, we've got this index all the way down here. So these are our data values. Let's just say we've got 20 of them. So what we're doing when we give it this index here, which is basically we're saying go to X and find us the value that's at position 136. Okay, and what that's doing is just basically saying go into our vector, which is this. Imagine I said I want to find the value at number 9. What it would do is it would go down and get this 4 here. Okay. So this is basically just the structure of what we've got. These are all the data points and each one of them have an index, and we're just saying give us the specific value at the certain point in the data frame. Okay, so that's how we get the first value, which is 4. And then what we want to do, because obviously we've got an even number of data points within our variable here, and obviously as we covered in the lecture, if it's an even number of data points, we're going to need to try and take the 2 central points and then average them. It's a lot easier if you do have an odd number of data points, as then you can take the very central data point in your distribution, but unfortunately we don't have that here. So this now is just saying, okay, go into my X variable. What I want to do is index into the point which is 136 and then add 1 so we get 137 and then basically return that value, which actually is also 4 in this instance, so that's fine. So in theory we wouldn't need to average them, but just because we want to do that to get the right answer here, we can add the 2 together and divide them by the numbers of digits that we've got, and that gives us essentially the median. Okay, so that is a roundabout way for calculating the median if you want to do it in a kind of incremental step approach. That's fine. If you're happier with larger expressions, we can do that as well in this way. So what we're doing here is we're saying, just give me the position, the data value at 136, as you've seen up here, or give me the data position at 137, as we've seen here. And then all we're doing is we're saying, okay, just add them together and then divide them by 2. So it produces exactly the same result as these multiple lines up here, but it does it in just one simple line. So that's kind of nice. Or, thankfully, R has a built-in command. So for a lot of these that I'm showing you here, I'm showing you exactly what the function is going to be doing under the hood, and I'm kind of breaking it down and making it really kind of clear, I hope, in a variety of different ways for how we get this answer. Once you know how we do this calculation, I would always just expect you to use the inbuilt function, because that's what they're here for. That's why we use a program like R to use inbuilt functions or other functions that people have built for specific purposes, so that it's just easier, it's far more efficient for us to actually do analysis. So when we actually run the median just here, we're then just saying find the median for my data set X. And this additional argument here, so this is just saying if it's an NA value, so not applicable value, just remove it. Okay, so it's saying if we've got any values that maybe are missing, maybe they're not numeric, whatever, just remove them for us. So this is just a standard command that you can place into the median function, and we're just saying in this case we want it to be true. Okay. So if you're stuck for the fact, well, how's Ed done that? How's he actually added in this additional argument? Well, actually, if you go to the help menu and you look for median, you'll see that all of the arguments are listed just here. And actually, if you look at the second argument, it's saying, you know, it's a logical value indicating whether NA values should be stripped before the computation proceeds. Okay, so that's just exactly what we've done here. So just remember, if you're ever stuck on any of these functions and you're not quite sure of how something's been executed, then just read the actual the help menu just here. Okay, great. So the arithmetic mean now, let's think about how we actually generate that. So you'll remember in the previous lecture, what I did was I showed you how you create a sequence. So if you just say, I want a sequence between 1 and 10, you use a colon. Basically, if you execute that, it's going to produce a vector of all the digits between 1 and 10. And what we can do is we can actually concatenate them together and then allocate it to a specific object, which goes into our global environment up here. So you'll see y has been allocated to the global environment, and now it contains all of those values that we created. Okay, so we would expect this to be 10 long because we've got 10 values in there, which is fine. So now we've just allocated that as well for the length of this let's pretend this is a sample, and therefore it's got lowercase n as the length of the data set. Okay. So how do we calculate the mean? Obviously, there's multiple ways for us to do that. So what I'm doing here is basically just showing that actually we could just get the summation of all of those values just by summing up all of the numerical digits within the brackets here and then dividing by the lowercase n value, which obviously is 10, and what we get as a mean is 5.5. Okay, so hopefully you can see that being printed down here to the console based on these numbers. Great, so that's one way to do it. The other way to do it, which actually if I was going to have to write the mean out if I was going to write it out manually, this is how I would have done it. Off the top of my head, I would just have said sum. So this basically just sums anything that you give it. So if you give it y, it's just going to provide the sum. I would just have done this. So we've got sum as the numerator and the lowercase n as the denominator, and that's producing the same mean, 5.5. Okay. And then finally, this is how I would do it if I was actually just using R and I was just tapping away doing some analysis. I would use the inbuilt mean function, and I would just provide it with y, and I would just say please ignore any non-applicable values that aren't numerical. Okay, so you can see just using the mean here we get 5.5. So that's fairly straightforward, and I think that you should all be comfortable with just generating a mean, I hope, because this is kind of I mean, you should be familiar with this metric previously, and actually here I've just showed you how to quite easily do it within the R code. So we did cover the weighted mean within the lecture, so we also want to know how to calculate the weighted mean. And here what I've done is I've just generated some temperatures. So actually what I did was, you can just ignore this here. What I decided to do was, let's say that it's February, March, April and May. And I changed these numbers because I wanted the data to be somewhat realistic, and I wasn't really happy with the number that was there before. So let's just assume in Fahrenheit, for example, in February it's on average 50 degrees Fahrenheit. In March it's 60, in April it's 70, and in May it's 80. And obviously we have different number of days for each of these months. Okay, so we have the temperatures and the days. And my question to you is, can you go out her way and find the weighted mean? Okay, so we covered this within the lecture. I explained that the kind of quintessential example for gathering the weighted mean is to use some temperature variable, maybe that's collected on average for a month, but then you actually want to look at what the average temperature might be over a longer period, and therefore you might want to take into account the fact that those months are actually weighted differently. So because there's not that many days different, the variation won't be huge here, but it would really matter if we were going out sampling and some of our groups had like 500 people and some of our groups had maybe only 100 people. we would want to take into account, therefore, the number of participants that we had in each of those potential survey groups. So how would we do this by hand? Well, obviously, if you remember the math, and let me go back to that, because in the other cases, they were quite straightforward, so we didn't really need to return to the equations. But here, what we want to do is find the x bar value. And to do that, we want to take the sum of the xj times by the fj values and divide it by the lowercase n, which is the total number of values in the overall data set. Okay. So what we're doing for the numerator here is we're taking the sum of the temperatures multiplied by the days, and then we're dividing it by the total number of days. Okay, so by hand what we're getting is 65.333 reoccurring for this first method. We could use the weighted function mean, so if you want to take more look at that, I'd recommend you to look at the help menu, go to the weighted arithmetic mean here. You can look through at the usage, the arguments, the details. But essentially it should just be producing pretty much the same number that we were getting via the manual calculation, which it is, which is good. And then I just wanted to prove that you couldn't just simply average the monthly averages without getting a different number. So here it's only a minor difference, but ultimately it's producing a different number essentially, because this is just trying to average across the temperatures without taking into account the different days. So if you had a much larger data set with many different people, then obviously that would produce quite a significant difference in the true mean, and that's going to be introducing all sorts of bias into your results unless you introduce the weighted measures, as I have done here. Great, okay, so just before we progress, I just wanted to highlight to you some issues that can occur with missing data. So it might not matter so much in these laboratories where I'm using the inbuilt data set. So all you're doing is you're just literally loading in a data set that's already built into R, it's already clean, it generally doesn't have any missing data, so you don't have to worry too much. But actually what you might have, especially if you've been collecting data yourself or whatever, is you might have some missing values, and therefore when you get it back, you might need to do something with those missing values. So here I've just loaded a vector as an example, NA, NA, and what I'm doing is just saying if we try to calculate the mean and it's got a missing value and we don't explicitly tell it what to do with those missing values, then it returns an error. Okay, so it returns a non-applicable, because it's basically saying we've got a bunch of numerical data that we want to sum and it's got a string in there or a missing value in NA. And it can't sum that, so the computer gets confused, or obviously it's saying it's a bad command, so it returns a nonsensical result. So what we need to do when we use NA is kind of go back to that argument which I mentioned before, which is where we explicitly ignore those NA values that might be introduced. I think also you might be familiar with these types of errors if you're using Excel and then you save something from Excel. So let me show you an example. If you do, let's say you've got a long number like this, and in Excel you have the actual comma here. If you save this down now as a CSV and you load it into R, it might not recognize this as a number. In fact, it probably won't recognize this as a number. It will actually think it's a string because it's got a character in there as the fourth entry point, so the comma. And this is like a classic way for you to introduce results into MATLAB or R, which crashes the program and won't work. It will return an error message, much like I've shown you just here. So if you do get that, then you just need to remember that you go back to the numbers, you just remove the separator and you just leave it as a raw number, okay, and export that as a CSV file into R. Okay, so I don't want to confuse you, but I just want to provide you with a good example of why you might need to use this. If you've got some values in your data set that aren't going to be able to be processed in the way that you would normally do with numerical data. We can also take the length. So here it's including all of the values that we've got, but actually if we use the NA omit, which is just saying give me it's actually just saying ignore all of those things that are NA, so not applicable within the NA data set. So when we take the length here, it's basically gone from 6 if we include the NA down to just 5 if we actually do the NA omit. And this is important because again it might introduce some bias into your analysis. Okay, so that's the missing data. Let's move on now to those measures of dispersion and variability that we covered within the previous lecture. So let's return again to the old faithful data set. And what we're going to do is we're going to, let me just clear the global environment so we can start afresh. We're going to allocate that eruptions vector of values into the global environment again as x. And to get the range, what we're going to do is we're going to use an inbuilt function min. So this just goes into x and says find me the smallest value that we have. And then I'm going to use the max value, which again is very straightforward. It just goes into x and just finds the maximum value that we have. Okay, so we've got 1.6 and 5.1. And actually then once we've got those two values, we've got the minimum value, we've got the maximum value, we can actually just subtract the minimum value from the maximum value, and then we should get the range in the data set, which here is 3.5. It's expressed in minutes, so 3.5 minutes is the range that we have within the data set. So that's how we manually do it, but the likelihood is that you might want to use the range function, which is just going to basically produce, it's going to return the smallest and the largest value for you. So you can specifically index into that range function. So here we're just indexing with a square bracket. It's just saying, okay, when we get range, what it's returning are two different values. If we index with the square brackets and a 1, it says just give me the number that's in position 1 in that set of return values. So you can see here 1.6, or we could say range, okay, out of those two values that return, give me the value that's in the second place. That's how we index the second place value. Or we could just do exactly what we did up here, basically, which is give me the maximum and subtract the minimum, and that should give me the range. Okay. So I think that we've had 1, 2, 3 different ways there for us to actually calculate how to obtain the range. Obviously, I did say in the lecture that the range isn't always the best metric to use because it's a bit blunt. If you've got outliers, then your range is going to be quite significantly skewed, essentially. So you remember that with the box and whisker plots that we looked at, there was a specific way within that approach that kind of recognized that there would be outliers and they're just kind of left to be where they are, but then we focus on trying to take the main distribution of data points, which is basically within the kind of interquartile range, and then a certain amount of distance either side of that interquartile range just to capture those main values in the tails, but while excluding the outliers. So how do we kind of do that in reality? How do we actually get quantiles from data sets? Okay, so I'm going to just introduce you first to this sequence variable. So let's have a look at it here. So this is just a way to produce a sequence generation. Okay, and you're able to state the numbers that you want to generate a sequence for. So here I'm saying give me a sequence of values between 0 and 30. Hopefully that's fairly straightforward for you to see. You can see all of the values being printed down here. What I can do as well is just saying, rather than give me 0, 1, 2, 3, 4 in full sequence, I can give it a third argument. And that third argument is going to say, well, this is a step function. So what I want you to do is I want you to go between 0 and 30, but I want you to actually do it in increments of 10. Okay, so if I have a look now at what this sequence generates, rather than 0 to 30 as we've done up here, it's just giving me those values in a step function of 10 units. So 0, 10, 20, 30. And actually this sequence function, I mean, you may be familiar with this already if you've used MATLAB or anything else like this, will work in any specific way that you're interested in. So it doesn't just have to be positive as we've done here from 0 up to 30. You can put 30 and say, give me a sequence going down to 0. And you can say that I want it to decrease in an increment of -5. So when you do that, it's going to provide you with something sensible in response. So 30, 25, 20, 15, 10, 5, 0. Okay, so hopefully that's fairly clear for how we're generating those sequences. And the reason why that's important is we want to be able to give that sequence basically as a set of quantiles to this quantile function that we're then going to use. So this just basically says, for the variable x that has all of our data points, produce me the quantile values, and we need to provide a sequence of those quantile values, and so this is going to be between 0 and 1, so 0 being the bottom of the data set, 1 being equal to basically 100, so the top point in the data set. And what we're saying here is we want this sequence to be, we want it to give us quartiles, we want the sequence to be every 0.25, so the sequence here you can see at the bottom here, it's giving us this set of breaks, and then when we actually allocate it to quantile and I run that, it's going to give us our quantile values. So 1.6 at the bottom of the distribution, 5.1 at the top, the median 4, and then we've got our interquartile range here. So from 25%, it's 2.16, up to the 75% value, which is 4.45. Okay, So you can play around with this as much as you like. So I did present some decile work that I've been doing. I like deciles because quartiles doesn't give you that much insight into the overall distribution. If you go to percentages, then in some ways it's like way too much information. It's a bit of an information overload, and it's really quite hard to plot. So I like deciles because you're able to capture all of those steps in the distribution, and it just gives you 10 segments to work with, so that's much more sensible. So we take our sequence of 0 to 1, stepping every 0.1, and then when we provide it with that, we get our decile values down here, okay? And you can do it as well with any amount that you want. So quintiles here, so for 5 different steps. Great. Well, that was an example of how we use the quantile function. We can actually get a whole load of this information if we just use the summary function. So if we go to help, summary, this is a classic one of those inbuilt R functions which just saves you loads of time once you know how to use them. So the summary function is from the R base package, and it provides an object summary. So you just have to give it a generic R object, and it will provide you with a summary of all the different things that you may want. Okay. So we can also get individual items of return data from the summary. So in this case, maybe what we want to get the mean value, which is 3.48, and then we can index into that returning set of data points with square brackets, and that's how we end up with the mean that we want, in case you want to specifically use that in a calculation, for example. Great, so that's the summary function. Box plots, hopefully you'll be familiar with these already because we've covered them in quite a few different places. Let me just go back to the box plot function. Here we go. So you'll remember that we had the whisker up here and down here, which is about 1.5 times the distance from the box. So that's how it ends up being calculated. The box represents the 75th percentile point and the 25th percentile point. And then this black line here, essentially, this is the median value. Okay, so we can see actually our data are quite skewed. Most of the data points are around here, around about 3.75 minutes. So 3 minutes and 45 seconds. But then we do have some that are incredibly short, but they're probably more outliers in comparison to the rest of the distribution. Okay, so let's move on to the standard deviation now. So you'll remember the standard deviation basically provides us with some understanding of the average dispersion around the mean. There's multiple ways for us to calculate it. What we want to do first is to actually get the X bar value, so that's the mean, so I can get that and place it into the global environment up here. Then what we want to do is actually take the length of the total number of data points that we've got, so let's just assume here it's lowercase n. And then what we're able to do is we're able to recreate that particular math equation that we had within the lecture notes. So what we're doing here is we're taking the sum of the squared values. So what we're doing is we're subtracting each value from the mean, that's the deviation, and then we're squaring them. And that's basically our denominator. So we're taking X bar from each one of the items in X. We're then squaring them, as I've just stated, and then we're summing them up, okay? And that's how we get that numerator just there. On the denominator, basically we are taking the full length and we're subtracting 1 because this is a sample. This isn't the total population, this is just a sample. I'll show you shortly why that matters. And then what we're able to do by using this is actually develop an insight into the standard deviation, which here is about 1.14 minutes. Okay, so that's the mean, so the average deviation around the mean value in the data set. Okay. We could just, if we wanted to, and you will probably do this by the time you become fluent in R, just basically use the inbuilt standard deviation function. So when we do that, SD, that just produces exactly the same number that we had before, okay? So if you want to go look in more detail at that SD function, you can just use the help menu if you want to, okay? Great. So you will remember that for the variance, essentially we're doing pretty much the same calculation, but we're not taking the square root at the end, so it's not necessarily put back into the same units. But it's interesting to know how much variance there is in the data set. In this case, we could just, rather than recalculating all of this again, we could actually just square the standard deviation if we wanted to, because this here is just it's the same, as I said before, as the standard deviation without having the square root taken. Okay, so that produces 1.3. And if we just use the var function, we get exactly the same number. Okay, great. So we're making good progress here. Let's move on now to the coefficient of variation. So you remember that all of the measures that we've used so far are focusing on using absolute units. So it's basically producing a metric which is pretty much always in the same units as the original data set. But that's not always that useful if we want to be able to directly compare different data sets, which may be measured in different units, for example. So what we want to do is to actually calculate the coefficient of variation. So it's a coefficient, so it's going to be between 0 and 1, and we can think of this as a percentage in many ways. So it might give us an indication as to the percentage data variation that exists within one data set against another. You saw just there that what we need to do is we need to take the standard deviation, and then we need to divide it by the mean and then times it by 100, and we can do that quite easily. So we can individually get the SD for x, or we could individually get the mean for x. So basically what we're doing is we're taking 1.14 and dividing it by 3.48, and this gives us a value of 0.32. So there's approximately 32.7% data variation within this particular vector that we have around the mean. So it's the relative dispersion around the mean value. Okay, great. Now for the different kind of shape and relative positions that we were interested in at the latter part of the lecture, we can't actually calculate all of those metrics using an inbuilt package, so we do need to install the moments package, which you can do quite easily. You just need to type install.packages and then place the moments in inverted commas. And then once we get there, essentially you just need to load that package, which is now installed on your computer. You need to actually bring it into the current workspace. So we just need to tell the library, okay, now bring in moments. You can see actually when that little stop button is up here, it's actually processing the loading of the package, bringing it into the workspace. So hopefully this is going to work, and this will load okay. Okay, so it's still, unfortunately, still processing. Apologies for my computer crashing. I'm sure you appreciate that, computers are temperamental at times. Okay, great. I just had to restart my computer and it worked fine. So it's actually just R that needed restarting. So I was able just to install Moments, the package we need, and then I was able just to call Moments and bring it into my working directory. Essentially what we want to do is we want to look at the skewness of the data. So this is going to give us some indication as to how symmetrical the data points are. What we want to do there first, if I just remind you of the actual equation, is we want to basically get the deviations, and then we want to cube them to get the numerator. So that's what we're doing here. We're basically subtracting all of the data values, or subtracting the mean from all the data values, and then we're raising them to the power of 3, and then we're summing them in order to get that numerator, which here is minus 167.2544. And then for the denominator, what we need to get is the number of data points that we've got, and we need the standard deviation cubed, essentially. So when we get the length of x and we get the standard deviation and cube it, we end up with the denominator, which, my apologies, that's because I restarted my computer. So why don't I just change this here so that it's clearer for you. Can you see that I've changed it so that now what we've got is the standard deviation of x, and then you don't have to worry about what s is. So this is basically taking the standard deviation, we're cubing it, multiplying it by the length of the data points. So now we've got minus 167 essentially as the numerator, and we've got 404 as the denominator. And then we're able just to get the skew by dividing the two, so which was the remaining operation that we had left from that initial equation. And that provides us with a minus 0.41, so it's giving us an indication there's a slight negative skew. Okay, and you can still use the inbuilt package that we installed, which was skewness, so that's the function from the moments package, so let me just show you that. Over here, so this is what we installed. The skewness of the sample is represented by this function, which takes either a numeric vector, a matrix, or a data frame. Okay, great. So we were able to reproduce the number that we obtained manually with the number that we obtained from the moments package. Now for kurtosis, you will remember that this relates to how flat the distribution is or how pointy it is. So we had these really nice kind of funky looking shapes over here where we had the platykurtic distribution, which obviously very flat. Remember that relates to platypus is the way that I remember it, which is a very flat animal. And then the leptoklirtic shape, which is incredibly pointy up here, far more than the normal distribution. And what we need to do again this time is basically produce a very similar equation. So we want all of the deviations, and this time we want to raise them to the power of 4. And then we want to divide them by the number of data points that we've got, multiplied by the standard deviation raised to 4. Then we need to subtract 3. Okay. So I've got right. Okay. Let me just show you how we're doing this then first. So to get the numerator, we just go through that very simple calculation that I just showed you. So let's see what number that we get there. So it's 687. We then need to get the denominator, very easy again, same process. We get 461, and then we can actually divide the numerator by the denominator to get 1.63. Okay, and we do have a slight difference here, and actually that's just because our function does not necessarily subtract 3 automatically. Okay, great, so that's how we generate the kurtosis. Okay, moving on to functions now. So we may want to get the skew, and sometimes we may want to do that using our own functions. So I think I covered this in the previous example, in the previous lecture, how we create our own functions. But having our own way to calculate skewness, for example, is a nice way to demonstrate this again. So that's essentially what I've done here. So we can declare the name of the function here, which we're going to call skew, and we're going to allocate the function to it, and then we're going to list the arguments that we want to give it. But the guts of the function, as I describe it here, is whatever goes between the curly braces, okay, so the curly brackets. So once you open it, that's starting the function. Once you close it, that's closing the function. And then you can basically go through and tap whatever you want into here. Then whenever you call the function, it will just run through whatever is actually held within those curly braces. Okay. So here we're just saying we want to be able to give it vect, which is a single numerical vector in this particular example. It's going to calculate the numerator, the denominator as we've done above, and then it's just going to return the skewness to us. Okay. And I just wanted to demonstrate before we get that this is a self-contained function, and therefore all of these variables that are defined in here are local to this specific function. It means that they're not available in the global workspace. So although we define numer here for the numerator, and we've entered the function into the memory, I can't actually access numer, okay? So it doesn't show up here in the global environment. And that's kind of that's not a bad thing. That's actually a feature. That means that you can state very complicated functions and then either have them in other scripts or call them whenever you want, but it means it doesn't chuck everything into the workspace, which is really nice. So once you've actually got that function, we're able to give it the x that we had before for the eruptions data and provide it with the skew, and it produces an automated estimate for the skew. So that's essentially what the moments package is doing under the hood when we install it and we load it and we load the skewness function. Okay, great. So that basically just covers everything that we've done so far. What we haven't done is me just show you why we end up using the number of degrees of freedom rather than the total number of samples in the data sample when we are trying to, for example, estimate a mean. So I just give you a demonstration of that here. So I'm talking about how when we sample from a population, the chances are that the sample will not have all of the extreme values. Okay, so imagine you've got a huge distribution of data and we're just randomly pulling 5 or 6 individual data points. I mean, there's no way that we're going to be getting into the tails of the distribution every time. There'll be a very small probability of that happening. So without these, what we basically end up with is a standard deviation that would probably be smaller, so less dispersed than the actual data. So just to make the standard deviation more closely resemble the actual population standard deviation, we always divide it by a smaller number. That's why we do the n-1, okay, to make the calculation larger. So you'll remember that I just briefly covered this. Why do we use the degrees of freedom within the lecture on this particular slide, particularly for smaller samples? But let me just show you why that matters. So if you go to the rivers dataset, so this is an inbuilt data package of the rivers and the lengths of all the major North American rivers, essentially. So this is going to be all the major ones all the way up to the Mississippi, which was most probably going to be the largest one in the data sample. So we've got 141 observations, and all the lengths are measured in miles. Okay. So once we've got that data, what we can do is the function SD calculates the sample standard deviation, so we need to do the population standard deviation. So I'm going to give you an example first of how we get the population standard deviation. So this is basically, in our data set, it's all the rivers, so it is the population. So we end up with 492 miles as the true population standard deviation. Okay, so this is the true standard deviation around the mean. But let's just take a 5-river sample, and when we sample this, as we do here, this is random each time unless you set a seed value, so it's just going to pull 5 samples each time that I keep doing it, and they're not going to repeat, they're going to be different every time, so there'll be variation in the numbers that we produce. But let's just say that we take a sample and we allocate it to the sample, allocate it to a vector called SAM up here. And then let's say that we take the population standard deviation. We end up with 109, okay? And then we end up, if we take the sample standard deviation down here, of 122. Okay, so you can see when we take the population, sorry, you can see when we take the sample standard deviation that we are actually getting closer to what the true value is. So obviously with 5 sample data points, we're not going to get anywhere near the true value. But you can just see as one example that by dividing by the n-1, we're getting much closer to the true value than just using the population standard deviation estimation. Okay, great, and you can repeat that many times, and you can play around with this and look at how the variation occurs at each time. There'll be some variation, but what's kind of neat about using computers, obviously using R, for example, is that you can generate thousands or tens of thousands examples of this particular differentiation, if you like, between the 2 different ways of estimating. So just to kind of show you in kind of a nifty way, what I've done is I've just generated a function which we've defined. It's a loop, and what we're going to do is basically we're going to place a lot of these estimates into a vector, and we're going to take the average of them overall, and we're going to look at what the values are. So this is something that I use all the time, the ability in a computer to loop through many, many numbers and record the results. So it's just a very small little simulation that we're carrying out. And the loop, basically, if you don't know what this means, it's just saying for I, which in this case is a number, let's just say it's 1, and then it's 2, and then it's 3. Basically, it will just loop all the way up to this top number here. So for I in 1 to 10,000, I will just take the form of each one of those numbers between 1 and 10,000. Okay, so we'll generate that 10,000 times, and each time I is generated as one of those numbers, we place it down here, and what we're saying is, can you just index it into P? So it's saying for the first time that we run it, when I is 1, it's saying put it into row 1 in our vector. When it gets to the second loop, it's going to be 2, so then it's going to say, okay, can you put it into the second row within our vector? And the point is that we can generate both the population way of calculating the standard deviation and the sample way of calculating the standard deviation, and each time we're going to place it into these two different vectors. Okay, so these are empty when we first generate them, and now this loop here is basically going to populate them. Okay, so I've just entered those into the memory now. Let me just show you that again. So when we put P and S here, they're just empty structures into the global memory. They're just saying we are logical vectors essentially, and we can take information when you generate it. And then what my loop here is doing is just basically it's generating a standard deviation, and then it's literally just putting it into the vector up here. Okay, so when we do that, now what we have is P and S all with those results that we've generated. Okay, so that's going to be very useful for us. Now what we can do is we can actually take the mean for each of these two different vectors. So you can see that the true standard deviation is 492. If we were to calculate using the sample approach, we would get 476, whereas if we're going to calculate using the population approach, we get 476. And if we calculated using the sample approach, we get 481. So my point is, by using the sample approach, we get a number that's actually much closer to the real true value, because we're basically taking into account the fact that we're not going to capture all of those extreme values when we're sampling. Okay, so hopefully I didn't confuse you too much in my explanation there. You've got the code. You've also got the slides where I talk about this and provide you with a detailed description of why we do this, to reduce bias in the estimation of that parameter. So hopefully now you'll be able to understand exactly why we use these different approaches for calculating the standard deviation. Okay, so I don't think that these are particularly complicated metrics that we're calculating here. Hopefully you understand this notation. Hopefully you know how to generate this now. You've got the code here for how you actually generate these metrics. There will be a lab assignment that obviously you need to complete in generating answers for these different metrics. So you need to look out for that. It should be on the Blackboard now for you to download. I'm going to leave things here. I just wanted to point to one issue that maybe some of you had when you were installing. So if when you try to access your R installation, if your RStudio hadn't automatically downloaded a version of R onto your computer, or if you didn't already have one, you might want to go to the R project for statistical computing and actually then just go to download a version of R. Okay, so you can just go to any CRAN mirror, you can click the R version that you want, and then when you get here, basically to download a certain version, you can just download this down here. And then once you get there, all you need to do is execute that file, load it onto your machine, and that should solve any issues that a few of you have been having, because you just had RStudio, which is basically just the integrated development environment. You still need the actual statistical computing package, which is the language basically. So once you've executed this and you've installed it onto your system, which should be fairly straightforward, then you should be able to load R up and get things going. Okay, so don't hesitate to reach out to me if you've got any further questions on that. And hopefully we're all now up to speed in getting all of the software installed. Okay, great. Well, thank you very much. It's nice to see you all, and I hope you have a good day. Goodbye.